So let's do an example. Problem 8, chapter 2. In this problem, we have a particle which is moving on the line. So we have a line, a particle is moving on this line. And it says the velocity of the particle is equal to a constant number k, which is 0.2, times root square of s. And s is the location of this particle from the origin. For example, the origin is here. From here to here is called s. If we know the location of the particle, we can use this equation to find the velocity of it. So we have some force here, let's say some electromagnetic force, something which gives the velocity as a function of s to this particle. So we have this equation for the velocity. And it says the velocity of the particle at the beginning is 3 millimeter per second at time is equal to 0. And we are supposed to find velocity, acceleration, and position of this particle when velocity goes to 15 millimeter per second. So what's going to be the acceleration, position, etc. So I'm gonna solve this problem in a more general case and find an explicit equation for the velocity, acceleration, and also the position of this particle with respect to time. So first of all, just to remind you, we had two types of equations. General equations, which I'm gonna list them here. The general equations were this: velocity is equal to ds dt. Acceleration is dv dt. And time independent equation is a ds is equal to v dv. So these are general equations. And we had three other equations, algebraic equations for acceleration constant case. So if the acceleration is constant, then we had velocity is equal to initial velocity plus a times t. Position is equal to initial position plus initial velocity times t plus 1/2 of a t squared. And the time independent equation was 2 times a times s minus s naught is equal to velocity squared minus initial velocity squared. We are allowed to use this equation only in the case that we know the acceleration is constant. Otherwise, we have to use these equations. So in this case, we know the velocity as a function of position. And we have some information about the initial velocity, and that's all. So is the acceleration is constant here? We don't know it. Probably it's not going to be constant, right? So because we don't know the acceleration is constant here, we are not allowed to use these equations here, right? So we have to use these equations. So I'm going to use any of these general equations in this problem. So we know velocity is a function of position, and I'm going to find an equation for position and also acceleration as a function of time. So what should I do here? If you look at these equations and think which one is going to be useful here, probably the first one is going to be the best option here. Why? Because we know velocity is a function of s. If I put it here, then I can separate the variables and integrate this and find s as a function of t. How? This is the way it goes. Velocity is equal to, from this equation, velocity is equal to k times root square of s. And from here, velocity is equal to ds dt. Now, if you look at this equation, we have only s and t in it. And I can separate these two variables. I'm going to have ds divided by root square of s is equal to k times dt. And after separating the variables, you can easily integrate this equation, right? So I'm gonna have integral of this one is equal to the integral of the other one. Time goes from 0 to any given time like t, and s goes from s0 to the current position at time t, right? So the integral of this part, integral of root square of s, is gonna be 2 times root square of s, right? Just to remind you, integral of x to the power of negative 1/2 dx is gonna be equal to 2 times x to the power of 1/2. Because if you take a derivative of this, you're gonna have 2 times 1/2 times x to the power of 1/2 minus 1, which is gonna be negative 1/2, right? So knowing that integral, then here we are gonna have 2 times root square of s from s naught to s. We are gonna have 2 times root square of s minus root square of s naught is equal to, the other side is gonna be just kt, okay? So if I wanna find s as a function of time, then I need to divide both sides to 2, then bring root square of s naught to the other side, then I'm gonna have root square of s is equal to root square of s naught plus 1/2 of k times t, and from here s is gonna be equal to root square of s naught plus 1/2 kt squared. So we got an equation for s. So at any time I know what is the location of this particle, but I don't know what is s naught. There is nothing is given about the s naught here. So I need to find s naught. How can I do that? I have a piece of information here that I can use it. We know the velocity at the beginning is 3 millimeter per second, right? And we know the velocity at any time is equal to k times root square of that. So at time is equal to 0, we know the initial velocity must be equal to, based on this equation, it's gonna be k times root square of the initial position, and k is given, is 0.2, and the initial velocity is given to is 3. So 3 is gonna be equal to 0.2 times root square of s naught. From here we can find s naught. S naught is gonna be equal to 225 millimeter, which I can put it here. And the square root of 225 is it should be 15. So yeah, it should be 15. So from here I'm gonna have s is equal to s is equal to 0.1 times t. 1/2 of 0.2 is going to be 0.1 times t. The square root of s naught is going to be 15. So plus 15 squared. Now I have the location of this particle as a function of time. Okay? And the good thing about this equation is, if I know this, I can take a derivative of this to find the velocity as a function of time. And also, if I take another derivative of it, I can find the acceleration of it. So velocity is equal to ds dt, and the derivative of this function is going to be 2 times derivative of inside it, which is going to be 0.1 times 0.1t plus 15. So it's going to be equal to, the velocity is going to be equal to 0.2 times 0.1t plus 15. So we found the velocity as a function of time as well. Now I can find the acceleration. Acceleration is equal to dv dt. So I need to take another derivative of this, which is going to be 0.2 times 0.1. So it's going to be 0.02 millimeter per second squared. And the unit for velocity here is millimeter per second. And the unit for displacement or the position is millimeter. Okay, so we got all the equations that we need. We found position, velocity, and acceleration of this particle as a function of time. The last part of the question is saying when the velocity is equal to 15, find the time and also find the position of this particle and also acceleration of it. Acceleration is going to be constant here. We didn't know the acceleration is constant from the beginning, but after deriving all the equations, we figured the acceleration is constant. And so for the last part, when velocity is equal to 15, I can put it in this equation to find time. Then after finding time, I can put it here to find the position, right? So velocity is equal to 15. So 15 is going to be equal to 0.2 times 0.1 times t plus 15, which we can find the time to be equal to 600 seconds. Okay. So after finding the time, I can put it in the position equation. Position is going to be 0.1 times 600 plus 15 squared. So S is going to be equal to 5620 millimeter. So when the velocity is equal to 15, time is going to be this, position is going to be this, velocity is going to be 15 itself, and acceleration is constant all the time. So acceleration is going to be 0.02 millimeter per second.